All right, practice exam 3. Problem 1, we've got the simple harmonic motion model of a spring is given by that equation. D is in inches, T is in seconds. Find each of the following, provide exact answers, and include units. So the maximum displacement from rest is just finding the amplitude. So it should be the absolute value of -8, which is 8, and inches, because those are the units we should be measuring here. Where that -8 comes from, that -8 up in the -8 cosine of 6 pi t. And the time required for one oscillation is, basically asking for the period. Period, of course, is 2 pi over b. So 2 pi over 6 pi, which again, we can pull right from that equation. 2 pi over 6 pi is going to simplify to 1/3. And that'll be in seconds. So 1/3 of a second is the time required for one oscillation. And finally, the frequency is 1 over the period. So 1 over 1/3 simplifies to 3. And this can either be oscillations per second or 3 hertz. Specifically, though, hertz is only the unit for inverse seconds. So if our time were measured in minutes instead of seconds, we just have to say oscillations per minute. But since it's seconds, we can use hertz, being that fancy unit. Cool, that's simple harmonic motion. All right, problem 2, a toy rocket is to be launched from the ground and aimed toward a big tree on the other side of a fence. If it's 21 feet from the launching position to the base of the fence is 9 feet tall. What is the minimum angle of elevation required so that when the rocket is launched, it'll clear that fence? So if we draw ourselves a triangle, kind of like this one, and we label some stuff on here. First, we're looking for some kind of a fence, or we're aiming at a tree. If we were so inclined to draw that in, here's a tree on the other side of some fence, where we know that the fence is 9 feet tall and we're standing 21 feet away from that fence. We're interested in the minimum angle of elevation required to get up and over the fence. So I'm trying to get this angle theta. And putting together what we know, well, we've got an opposite side and an adjacent side. So we should have tangent of theta is equal to opposite over adjacent. So 9 over 21, or 3 over 7. Meaning that theta is equal to the inverse tangent of 9 over 21. Let's scooch that over a little bit. Which comes out to a number. Let me go get that real quick. Arctan 3 over 7 in degrees. So 23.2 degrees. And then we want the minimum angle of elevation in whole degrees that gets over, so 24 degrees. It's going to be our answer. So this question has a bit of a tricky wording to it. So normally 23.2 degrees. If I rounded to the nearest whole angle, that should round to 23. However, it asked for the minimum angle in whole degrees that gets over the fence. So even though if we rounded 23.2, we would round down to 23 degrees. 23 degrees is just too small to get over the fence. So because it asked for the minimum angle, we'd actually round up no matter what the decimal is in this particular case. Most questions aren't asked that way, but this one had a bit of a fancy wording to it. So I rounded up to 24 degrees because I needed the minimum angle rather than the nearest whole angle. Okay. Next, I'm trying to get the cotangent of the cosine inverse of negative 63 over 65. So, starting with the initial piece, I've got the cosine inverse of a negative number, which means that I'm going to be in quadrant 2. Right, since I'll be looking at, the cosine inverse of a number is just an angle. Seems like we've usually been calling it alpha in the notes. And again, that's in quadrant 2 because it's cosine inverse of a negative number. So we'll put our coordinate axes on here. That red angle right there is going to be alpha. And if we label the stuff that was given to us, negative 63 is the adjacent side, which means 65 is the hypotenuse. And I can use the Pythagorean theorem to put those two pieces together to get the missing side. Y squared plus 63 squared is 65 squared. Seems like 12, or is it 20 is the missing side? 65 times 65 minus 63 times 63. Oh, it's 14. So yeah, y squared is 256, and by 14 I mean 16. Yeah. So y is plus or minus 16. We're in the second quadrant, so we're going to take positive 16. Finally, we need the cotangent of alpha. So putting together what we have, cotangent is adjacent over opposite. So negative 63 over 16. That would be our final answer. So real quick, going back to the problem before, we had a question in class. why don't we just use regular tangent in question 2 as opposed to tangent inverse, which is what we actually used? So anytime we use a regular tangent function, or regular sine or regular cosine for that matter, it always takes an input of an angle and an output of some ratio, some number that is a ratio of sides in a triangle. So if I know an angle already, then I'm going to use a regular tangent, a regular sine, a regular cosine, plug it in, get a number, and then use that number somehow to solve the problem. If I don't know the angle, meaning that the angle is part of the solution to the problem, that's when I'm going to want to use an inverse tangent function. Because the way that inverse tangent works, or arctangent, is that it takes an input of some number, and its output, the answer that it gives, is an angle. So if I want to know an angle, I use an inverse function in order to get that angle, because I know I can plug something in and it spits out an angle. And if I already know an angle, like we did in the first 8 weeks of class, then I would use just a regular function instead. But yeah, so because I'm looking for an angle, that means I know I need an inverse function instead of a standard function. All right. Then the multiple choice section of the practice test. Keep in mind that the real test is, well, it's all multiple choice. Circle the correct whatever thing. So we want the secant of the tangent inverse of square root 3. So this will be the secant of pi over 3. Since the tangent inverse of square root 3 is pi over 3. And the secant of pi over 3 is 1 over 1/2, or 2. All right. Problem 5, we want the arc sine of tangent pi over 4. So this is the sine inverse of, let me just go make sure I'm color coding this thing right. Yeah, this is the sine inverse of -1. All right, tangent of 3 pi over 4 is going to be -1 because we're in the second quadrant of 3 pi over 4. So it should come out negative. All the tangent values of a something pi over 4 are 1 or -1. And again, we're a second quadrant, so -1. And then we want the sine inverse of -1, which is negative pi over 2. So option B. So don't let option E trick you, the 3 pi over 2, because while the sine of 3 pi over 2 is -1, and that is the number that we learned off the unit circle back at the beginning of class, or at the beginning of the semester, when it comes to sine inverse, it's only defined down at negative pi over 2. So make sure you use the negative fourth quadrant when it applies for this set. Problem 6 is also a bit of a trick question. Find the exact value or possibly values of tangent inverse of -√3 over 3. And in order to make tangent inverse a function, there should be only one solution. So anytime we have an inverse trig function, there's always only one solution. So again, the wording is there to be a bit of a trick. Tangent inverse of -√3 over 3 has only one answer, and it is negative pi over 6. Uh, if some of these are giving you trouble, just getting the tangent inverse of the basic trig functions or sine or cosine inverse, just the basics, keep in mind that there is that practice inverse trig quiz that you can attempt as many times as you like. That's on D2L. So that's always there if you want to go practice that before the exam. All right, the cosine inverse of cosine of pi over 3. It's going to come out to just pi over 3. Let's talk about why. The cosine of negative pi over 3 is the same as cosine of pi over 3, but that doesn't super matter. Cosine of pi over 3 is 1/2, or cosine of negative pi over 3 is 1/2, and the cosine inverse of 1/2 is pi over 3. Those are the steps that we'd take to get there. And then in problem 8, we've got similar triangles. ABC and PQR are similar triangles. So find the length of side B, where side B must be this side, because it's going to be opposite angle B. So if we set up our ratio over here, B over 2.7 is equal to 8.1 over 3, meaning that B is equal to 2.7 times 8.1 over 3, which is going to be equal to 7.29. So if you wanted my method for getting there, I took 8.1 divided by 3 is 2.7, because those all just look like multiples of 3. So that's not too tough of some math to do there. And then I have 2.7 times 2.7, which is going to look a lot like 27 squared. And if you happen to know, 27 squared is 729. But since it's 2.7, we'd move the decimal place and get 7.29. So that was my mental math of getting there. You can always just use a calculator. Just throw all that in and see that you get 7.29 to come out. Okay. For problem 9, we have an object attached to a coiled spring is from its rest moving down a distance of 9 millimeters. Assume the motion is simple harmonic with a sixth of an oscillation per second. The equation that relates displacement d of the object is given by which of the following? So first thing we're going to look at is from its rest moving down. This means we're looking at a sine graph. Because it's moving down a distance of 9 millimeters, A is going to have to be -9. So between those two things, I can get rid of a lot of stuff. Anything with cosine in it is out, because I knew it had to be a sine graph or a sine equation instead of a cosine equation. And then also, if there were anything that didn't have -9, I could get rid of that too, but all the options are -9. So we just have to decide what the correct value of B should be, what the correct value of B is. Don't need too much alliteration there. So if I'm looking for B, well, I should probably start with finding the period. So the period is 1 over f, so it's 6, 1 over 1/6, 1 over the frequency, which means that b is 2 pi over 6, or pi over 3. Which means that option E is the one that we want. Circle that 1/6 because that was the other thing that was important. All right. Problem 10. Here we have one of our application kind of problems. We've got a runner beginning at the starting line of a race is going to proceed in the direction of 72 degrees west of north for 3.5 kilometers until she reaches refueling point. She then turns 90 degrees southward, running 6.5 kilometers to the finish line. What's the bearing from the starting line to the finish line? All right, so let's try and track this runner's path. So let's actually start by getting, we're going to be running northwest, which means left. So I'll draw my north line right there. And then if I want an angle that is 72 degrees west of north, that's going to be this 18-degree angle here. Hey. We're going to run for 3.5 kilometers that way, at which point the runner turns 90 degrees southward, which does not mean 90 degrees due south. It just means 90 degrees in the southern direction. Ooh, hey. And then it's going to run for 6.5 kilometers this way. So it should be a fair bit longer than our 3.5 kilometer line. And that's our runner's path. Let's actually shrink this guy down a little bit. Hey. Just have that thing be drawn a little bit more to scale. All right, and we've got to get the angle or the line that connects these two pieces together. All right. We'll have our little line right there. Okay. So label a few other things. This was our starting line. This is our finish line. In the end, we're interested in what? The bearing from the starting line to the finish line. So if we put what we know into this diagram, we started off at a bearing that was 72 degrees west of north. So this angle is 72 degrees. In the end, we're interested in the bearing from the starting line to the finish line, meaning we're after this angle beta right there. And furthermore, we have this angle theta that's on the interior of our triangle. And we've got a right angle over here with a couple other things. We know that we are going to run 3.5 kilometers in that first stretch, and the second stretch of our race is 6.5 kilometers. So, putting all that together, let's move that a little bit over to the left so I've got some more space. We should first notice that if we add up the three angles listed in the diagram, we should get up to 180 degrees since they'll add up to be a straight line. So that's looking at our original bearing of 72 degrees plus our interior angle theta plus our missing angle or our bearing angle beta. So if I want to know what the bearing angle is, I'm going to need to find that interior green angle first. Fortunately, we have the information to solve for that angle. It is on the inside of a right triangle where I know both the opposite and adjacent sides. So once again, we'll be looking at tangent of theta. I know that tangent of theta is, well, it's going to be opposite over adjacent. So 6.5 over 3.5, meaning that theta is the inverse tangent of 6.5 over 3.5. Move that off the page counter. So we'll take that to our calculator. Arctan of 6.5 over 3.5. Apparently this is something I've searched for in the past. And that comes out pretty cleanly to 61.7 degrees. In fact, it's 61.70 degrees. All right, bring that back up to the work where we were solving for beta. And we should have that beta is equal to 180 minus 72 minus 61.7. And if we put all that into a calculator, let's see what we get. I got 46.3 degrees. All right, now after all of that, I have my bearing angle. I just need to put it into a bearing. So 46.3 is the angle, and I just need to attach a cardinal direction to it. And if I go from the starting line to the finish line, that is a southwest direction. So our bearing should be 46.3 degrees west of south, or south 46.3 degrees west, or depending on how you want to read that bearing. All right. Let's take that to the next problem. So, which of the following correctly lists three asymptotes of y equals 53 tangent of 2x? So, if I want to find asymptotes for tangent of 2x, I'm going to take 2x and set it equal to pi over 2 plus k pi which would be the same thing as pi plus 2k pi over 2, just to get it as a single fraction. So x then is pi plus 2k pi over 4. So if I start picking some values for k, let's start with 0. I'm going to get pi over 4. If I pick 1, pi plus 2 pi is 3 pi over 4. And then 5 pi over 4, 7 pi over 4. I think you can see the pattern. It's just going to be odd multiples of pi over 4. This is for, shrink that down, move it a little bit. Maybe move this stuff up a little bit too. For k equals 0, 1, 2, 3, and on like that. So we wanted the one that matches up to some of these asymptotes, which is going to be option C. All right, problem 12 just asks us to fill in a table for tangent, secant, and cosecant, which is even all listed on worksheet 8. So this one shouldn't be too big a deal. So tangent, we know it has a base period of pi, while secant and cosecant have base periods of 2 pi. The range for tangent is all real numbers, while for secant and cosecant, it's everything except the open interval, -1 to 1. Keep in mind that we should be using brackets on -1 and 1, because those are both 1 and -1 are included in the range of secant and cosecant. It's I don't make it a huge point, but I know that there was a quiz question 2 weeks ago where you had both for just the base range of, I think it was secant. There were two options that were -infinity to 1, union 1 to infinity. One had open parentheses on the ones, and the other had brackets on the ones. So I didn't make it a point when you actually had to transform the range, but when I was asking for just the, the basic range and sort of in its purest form, I did make a distinction between the brackets and the parentheses. So make sure you pick the brackets because they should be included. And then we want the general equation of the asymptotes in terms of some integer k. We already did it for tangent in the previous problem. X is pi over 2 plus k pi. And that's the same for both tangent and secant. But then for cosecant, it's just x equals k pi. Cool. That's the whole table. Again, you can find that just on worksheet 8. And the one function that was left off that previous table was cosecant. So we're going to do cosecant expanded out in problem 13. So what do we want to do? Period, phase shift, range, and general formula for the transformed asymptotes. So for that period, I want 2 pi over b, which is going to be 2 pi divided by pi over 3, which is 6. Then the phase shift is c over b, which is positive pi over 6 divided by pi over 3. And that's going to simplify to 2. Oh, wait, no, I'll take that back. That's not going to simplify to 2. That's going to simplify to 1/2. Right? Yeah. Yep. So it'll be pi over 6 times 3 over pi. Yeah, I'm cool with all that. Okay. So then we want the range in interval notation, which is where that 10 is going to become important. So negative infinity to negative 10 union positive 10 to positive infinity. Might look cleaner if I just move it right there? Probably. No. Put it in the answer box. All right. Then we wanted a general formula for the vertical asymptotes, which means looking at the interior up here. So I want pi x over 3 minus pi over 6 to be equal to k pi. And we're going to solve this thing for x. Doing so means I've got pi x over 3 is equal to pi over 6 plus k pi. I can divide a pi away from everything. So x over 3 is equal to 1 over 6 plus k pi, or plus k, just regular old k, and then multiply both sides by 3. So x is 3 over 6, which is 1/2. Let's try that one more time. 1/2 plus 3k. So 1/2 plus 3k goes up there. Well, and it looks like that's the end of the practice test. All right.